Okay, let's start. I guess most of the class which is missing is probably done with the homework, so. Huh? Yeah, I will. You're looking for extra credits, right? Okay. Um, so, yeah, and you have the knack of walking out just at the right time. Okay, so firstly, any questions on the homework?
Yeah. So my Verilog stuff isn't working right now, but so I'm just working on trying to make the read enable on for only one tick.
Mm-hmm.
And so I don't really know if send and enable, then I want to turn it on. But then I don't know how to kind of ignore the send and enable for the rest.
So let's try something. All of those guys sitting at the back, why don't you move to the front so that we can interact? You also. Come to the front, very front. Plenty of seats there. Huh?
You're making engineer social.
Yeah.
This is scary stuff.
Yeah, that's fast.
You can sit here, there are seats on side. Yeah, go ahead.
You want to do it? Okay, let's just okay. One class, one class.
Okay. So firstly, the good news is we have at least one working design, which was just demoed to me. And I don't know anyone else has working stuff. You two. So two. Kind of, three, kind of, four. Okay. So that's a good sign. Anyway, midnight means for me the end of Friday. So those of you saw questioning the midnight interpretation, although according to Stack Overflow, I guess it should be Thursday night. But anyway. Huh? CCLE does not let me specify down to minutes. So so it's 00 on March 7th. Okay. Okay. So let's start with. So from the questions that I gathered, and I'll come to your question also. There are a few things that I just wanted to sort of get, just make sure that all of you kind of understand. Okay. So number one, in finite state machines, through the state transition diagram or state transition table, what you are specifying is on every clock tick what is happening. Okay, on every clock tick, what is the next state I'm moving to. Actually, I'm asking everyone to sit on the front half. Oh, okay. So if you could please. So every clock tick, a transition takes place. So if you are in a state, let's say, in my state diagram, I have a state and I have some transitions, maybe some self loop, some outgoing transitions. What that means is on every clock tick, so if I'm in this state, on the next clock tick, I'm going to evaluate whatever the conditions are associated with these transitions and make that transition. If I want to stay put in the state, I have to explicitly arrange for it. So for example, let's say I have a wire, and I want to get some sequence of bits out on it. Let's say I want the pattern 101. I cannot simply say x equal to 101 binary. Okay, that doesn't mean anything because x is a single bit signal, and I cannot assign 3 bits to it in one go. So if I want to achieve something like this, I will somehow have to arrange that I go through perhaps, for example, 3 states, in one of which x takes the value 1, next time it takes a value 0, next time it takes a value 1. That could be one approach. There are other possibilities also. So the state diagram is only giving you, or the state table only tells you what is happening in every clock cycle. What are the outputs and what is the next transition. Every output has to be specified. So there was another question along the lines that I don't want to output anything. That doesn't mean anything really, okay, because it's a set of wires, and at all times there has to be some value on it. If you don't specify anything, FISM is going to, folks, I'm asking everyone to sit in the front part so that we can have some interaction for a change. So there are plenty of seats in the towards the walls. So okay, so every at all times there is some output on every wire, and when you are designing a state machine, you are specifying what the inputs and outputs are. So for example, if I have, in this example, I have a 1-bit signal called X, then X is going to have some value at all times. If you do not specify it, then FISM will put in a default, but it's a bad style. So like I've said earlier on, you should always specify what is going on. And likewise, at every clock tick, there is going to be a transition. At every clock tick, depending upon which state you are in and what the inputs are, there will be some next state, which could be self, like you stay put, but there is a transition taking place. And likewise, you cannot, without something explicit on your part, you cannot say that, oh, I'm going to spend, I want to output a sequence of bits, I'll just stay put, specify x equal to 101, and somehow the state machine will just output that sequence. It's not going to happen like that. You have to specify, essentially instruct the state machine every clock tick what transition is happening, and every clock tick what the output is. So some of you may have seen this exchange of email with, I don't know whether the person is in the room or not, but if I have a syntax like this, let's say x3:0, and I say it's binary 1011. Let's say if I have something like this, what this is really saying is I have a signal called x, which has 4 wires, so it's a 4-bit signal, and at all times those 4 wires are going to have some value. And if in some state, let's say in a state like this, I wrote something like this, all that means is while I'm in that state, the 4 wires have the value 1011. Okay, it's not saying anything about sequencing over time. So you get to dictate what the inputs are, what the outputs are, and you get to dictate how they are changing. Okay, so everything has to be explicitly stated.
Is there any way to make part of the data path not count as an explicit input?
Part of a data path not count as an explicit input? Okay, I don't get the question.
So say you have you take your ASCII and you convert it through your previous project into the Morse code that we were using before. Is there a way we can have that count as like a input to the state machine, but we don't want to draw explicit like inputs, because then that means that our self loops back become very, very arbitrary.
Well, what you could do is, so firstly, no. So there has, I mean, if state machine is operating on an input, there has to be an input signal. Okay. Now, it could be that you are really seeking to, let's say, for example, you have multi-bit signal in your data path, but you're really interested in that, let's say that is all 0, for example. So then what you'll do is put an OR gate also in your data path and then bring out that 1-bit signal instead of bringing out the entire multi-bit signal. So you can optimize along those lines, but bottom line is if you're using FISM, through the dialog box, you have to specify what are the inputs, what are the outputs, and clock has to be one of the input. In fact, there was someone who was having problem with the Verilog, and at the very end the message was clock was not specified as an input. So clock has to be specified as an input, otherwise Verilog has no way of knowing that you intended that there is a signal called clock and that you intend it to be used within the design. And likewise, if you have a reset signal, again you have to specify it in the input panel. So in the input panel within FISM, you have to list all the signals which are coming from the outside world, as well as all the signals which are coming from your data path. All of those have to be listed, and likewise all the output signals which are going out to the world, as well as all the output signals which are going to the data path. All of them have to be explicitly listed. So FISM does exactly what you would do manually given a state diagram. Okay, I mean, it does not do any more interesting stuff under the hood there. Okay.
Is there something that we?
Go ahead. First you, then him.
So if we want to do the state diagrams by hand, because we built a circuit and then built a state diagram to like do the ideas, is there something we can use to notate, like saying, if everything else is not true, then self loop back? So we don't want to explicitly
list. Yeah. I would, for hand-drawn diagrams, you can always write else or something like that. Okay, so as long as the intent is clear, is fine. In FISM, you cannot get away with that. Okay, so hopefully that kind of answers that. So again, reasonable interpretations we are kind of open to, or likewise, for example, if you can take shorthand notations if a set of values, if some input takes a set of values and you want to transition, you can use a set notation or something, and that's fine, because then we are looking at it as a human. With FISM, you cannot do that. Okay, so first the question back there. Okay, cool. And
You said that we kind of assume that the clock ticks for the MCT and MCR are in line.
you cannot assume that.
Can we assume that they will never be in line?
So they are identical frequency.
Uh-huh.
So if they have a shift, that shift will always be there. But it would be a scary design practice if you are actually relying on relative clock shift between the two. You don't need to. Okay, just think of them as that you are doing a state machine, you're observing the signal. Okay, and think of it this way: if they're identical clock frequency, and if the MCTX is changing a signal, then it's going to be stable for at least a clock cycle, and therefore receiver will have a clock edge somewhere during that clock cycle, right? I mean, they're identical frequency as far as this assignment is concerned. So that constraint is actually really a very loose constraint. There is nothing. I mean, if it makes you happy and that the two are identical clocks, design like that. Your design will likely work almost 100%, close to 100% should work, unless you're doing something pretty weird with the clocks.
If your clocks are out of phase by family,
Yeah, so let's say the clocks, let's say transmitter had this clock. Okay, and they're identical frequency. The other clock is going to be some phase shift, but it will remain the same throughout. I'm not dynamically changing anything. Okay, now what will happen? So again, this is the TX side. So the transmitter is going to be changing signals. Those signals are going to change, are going to be stable between successive edges at the very least, and therefore during this interval, there is going to be some point in time where the receiver is going to see an active clock edge. So that will work out fine, really. Okay, so there's a question there.
Yeah, it's kind of on the same note. Can we assume that the clocks that we would give it in the main routine are going to be used for all of the testing?
Yes, they are identical. They are set to identical frequency.
Yeah, they have the same period.
They have the same period.
Different durations of high and low bit.
They have different duration of high and low bit. That's correct, but you should. It should not matter to you. So we do reserve the right to change the relative duration of high and low bit, but it should not matter to you. Okay. Let's see. Well, you asked my question. No. Okay, go ahead.
Oh, I'm still kind of confused on what the inputs send and available are supposed to do in the MCTX.
Okay, so let me pull up the design so that I can also walk you guys through that. Okay. Okay, so what is so firstly, what is happening out here is the following: the two modules that you are designing are the MCTX and FCRX. Okay, keyboard and TTY are from the library itself. Let me see if I can. Okay, and this module is a test module. It's called the tester, which I have created so that we can interface our testing circuitry to it. Okay, but really, what is happening is, so let's if you haven't been curious thus far, just look at what the tester is doing. So tester really, on one hand, is connecting to your MCTX and MCRX, and on the other hand, it is connecting to the keyboard TTY, and it also brings out some signals externally. So again, if I go back to the external world, you would see that these signals like data in, send, avail, test, enable, and all, they are, and likewise these signals, these are coming to the outside world. And what we are going to do is we are going to set test enable to be 0 or 1 depending upon whether we are testing your design or not. Okay, so when we set test enable to 1, then your keyboard will not be the one feeding characters to your design, but rather we will be feeding inputs to your design. You'll be interacting with a fake keyboard that we would have, which will behave similarly. But let's say the test mode is 0. Test enable is 0. Now what's happening? Let's look at the keyboard. So the keyboard has a clock. Clock is just tied in as it is. It has these signals. So there is a so this is the read enable. 0 disables the clock. So this signal means that if this signal is 0, then the clock is ignored. Then we have available, which is high whenever the buffer contains characters. Okay, so if the keyboard has a buffer, if the buffer is empty, then available is going to be 0. Otherwise, available is going to be high, and the frontmost character is going to be visible out here. So this is my ASCII, 7-bit ASCII coming out. Okay, so the way this keyboard gets used is that if there is something in the keyboard, then the frontmost character in that buffer is being output, and it will keep getting output until a clock edge is encountered during which clock was enabled. Okay, so for example, if this read enable signal was 0, then nothing will change. You will keep reading the same character. But let's say I made read enable high for 1 clock edge, 1 clock cycle, then a clock tick will come and the current character will be thrown out, and if there is a next character, that will appear out here. If there was no next character, then the available signal will go down to 0, and I think the keyboard's behavior is that it outputs all zeros at the time, so that's kind of the default value. So the way to use the keyboard is that your design, whenever it needs to read a so your design always has access to the frontmost character, okay, but whenever it needs to say, okay, I'm done with this character, throw it out, give me the next character, then what you will do is you have to raise this signal for 1 clock cycle, and then the buffer, the frontmost character of the buffer will move away. Now if you notice out here, this line, like the read line or these lines, they are all going to my tester. But inside the tester, if you look, what's happening? So let's look at the read enable. Okay, so the read enable line is coming from the MCTX, that's your design, and all my tester is doing is forking it out. One of it goes to the keyboard and the other goes to the external world. Okay, so this way it's almost like I'm creating a tap point. Okay, I'm able to observe the output of your design. Let's take available X. So what available X is doing is there is an available coming from the keyboard and there is an available coming from the outside world. And what I do is I have a multiplexer, and this multiplexer is connected to my test mode signal. So if the test mode signal is 0, then the available which is coming from the keyboard is the one which goes to your design. If test mode is 1, then available which is coming from the outside world goes to your design. So this way we can test your design and then essentially replace the actual keyboard by kind of something that we'll basically feed data from. It will emulate a keyboard. Question? No?
Yeah.
Okay.
Can you go back to the main? So you're saying even if we don't press send, if you type something in the keyboard and you don't press send, the keyboard will be outputting the first character, the leftmost character.
Keyboard's behavior is that at all times, remember this is an output, or at all times there has to be something on it. And what keyboard description says is that at all times, on those 7 bits, the frontmost character in the buffer is displayed. If there is nothing in the buffer, 0 is displayed. Okay, and this available signal tells me whether there is actually a valid character there or not. Okay, now so notionally, kind of the idea is that when the user press the send button, so in your state machine, you're going to monitor the send signal. So again, send is also going through my tester and feeding it to MCTX. Okay, if you look at in the tester, the send signal out here, sent from the keyboard, or rather the button, and the external will go through a multiplexer to your designs, and the test mode is the button which kind of feeds to your design. Okay, so the idea then is that the user presses the send button. At that time, your state machine should start reading character by character from the keyboard buffer, read one character, ship it out, read next character, ship it out, until the buffer is emptied. So that's what you would have to do. Okay. There's a similar behavior on the other side. MCRX, except the behavior here is simple. So if you look at the TTY, it has a clock signal. Again, clock you don't have any control over. There is a data line. I think this is probably the data line. No, this is write enable. So there's a write enable signal, which again comes from your MCRX, routed through the tester. And then there is a data line, which is this guy, which is the 7-bit ASCII character. So what's happening is that the way the TTY works is that at every clock tick where write enable is high, it reads whatever is the value out here. Okay, so whenever you so your strategy is you're going to put the value out here, and if you want the TTY to read it, you are going to raise write enable. If write enable is tied to high, then at every clock tick a new character will be fed in out here. Okay, and it will keep going into this. So you have to exercise control over write enable as well. Go ahead.
Yeah, I have a question regarding like the space convention.
Sure.
With regards to the display of the TP1.
Uh-huh.
Say I were to input at the keyboard EE-M16 space data design. Would it,
Oh, hyphen is not allowed, so
yeah, as it's not allowed. So in terms of it being displayed on a TTY, should it just be EE-M16 like one word or EE space M16?
again, we will never feed you hyphen.
Okay, so I'm not worried about.
You don't have to worry about
Okay,
there being spurious characters. Okay, so the only characters which will be typed there are going to be the 26 times 2 lower plus uppercase plus the 10 digits plus the space. Now space does present an issue, and which there was a thread on Piazza. So the issue that space presents. So firstly, Morse code does not distinguish between cases. So whether I'm typing lowercase or uppercase, you can only send the 26 letters. So on the TTY side, just print everything in uppercase. I think that's what I had specified in homework 2. We are just using that. Okay, so whether the case is lower or upper, everything appears on the uppercase. Now let's take the space. The problem is how do Morse code doesn't provide a symbol for space. So you have two options. One is you can say space corresponds to what Morse code calls as the interword spacing, and the interword spacing is 7 zeros. Okay. There are two problems with that approach. One problem, which is when I'm not sending any message, I have a single wire. I'm going to be sending zeros over it. Now, are all those zeros a sequence of spaces, or are they no transmission? I cannot distinguish between no transmission and sending spaces. We are going to accept that what might be nice though is that if you are getting a whole bunch of sequence of spaces, you only type one space out here, because otherwise what may happen is in between messages, my message will appear out here and it will just kind of disappear. But we'll be tolerant of whatever interpretation you make. I'll continue. And there was a suggestion by someone that maybe map space to some unused Morse code. That is fine too. Okay, so you can distinguish between space, the character typed on the keyboard, versus no transmission. No transmission is just sending out zeros, and space, the character, you can have a new Morse code for it, but that's a decision you can make. So first you, and then you, yeah.
Okay, so the key thing about the spaces, before you press send, and you're still, you're getting, the receiver's still getting 0, 0, 0.
It's getting zeros, yeah.
So, is it alright to make the receiver transmit only if it gets the first one? Like, it needs a 1, and like all characters begin with 1, right?
All characters will begin with 1. That is correct.
So, until it receives a 1, it outputs nothing.
Correct. So another way of saying is the following, that in between two messages, I have a whole bunch of zeros, potentially thousands of zeros coming in. I'm going to ignore them. Okay, so that's one strategy. The other strategy is you're going to say, I'm getting a whole bunch of zeros. There are a whole bunch of spaces because I'm thinking of interword space as 7 zeros. And in which case, your TTY will see a whole bunch of spaces, and we will accept either.
But if we if we say that any more than 7 zeros is just the same as 1 space.
Correct.
But then, if we have, is it possible that your input has like A space space space?
Right, exactly. So you will lose that ability. So on the Piazza, when I replied that if you use the strategy that space means 7 zeros, then if I have something like A 7 spaces or 10 spaces B, then output would be a single space and a B. Okay, so spaces will get coalesced. Whereas the other strategy, which was suggested by someone, was that we map space to a specific unused Morse code. Then, if I have 10 spaces, I can still recreate 10 spaces. Okay, we'll accept either, whichever direction you're picking. Okay, I don't know which order things were. You go ahead. We'll come to. Oh yeah, you were raising your hand. You're okay. Okay, so.
So if we do map the spaces to another set of Morse code, does that mean that the requirement for 7 spaces being a space, or 7 zeros being a space, is that like null?
It's basically gets nulled now. You're correct. Yeah. It basically, so because space essentially becomes a special letter.
Okay.
Yeah.
I didn't know if we had to somehow do both.
No, you in that case it will get nulled.
And you said
Okay.
you'll accept that?
We'll accept that.
Okay.
Okay, so if you are mapping space to the space typed out here to a special character, then okay. Now the thing to watch out though is in between two transmissions, right? I mean, I pressed the send, the keyboard buffer got emptied, and then I typed something and press send again. Then from the end of the first transmission to the beginning of the second transmission, now at that point you do have a valid 7 space thingy. 7 0 thingy, right? So that's one place where it will appear still.
Within the two circuits, MCTX and MCRX, do you want us to use a given clock, or can we like create other clocks too?
We would like it to use just these 2 clocks. So there's one clock. So as far as you're concerned, there's a clock coming from outside. Yeah, don't create internal clocks. You don't need to really. Is there a reason you're asking that? Oh, okay.
So let's just say keyboard plus A B C D space E F G, and then we plus send. So the output will be A B C D space E F G and then space.
A, B, C, D, E, F, G, and then at least one space, depending upon the design approach you are picking. If you are picking the design approach of mapping spaces to special character, then after the last character of the first transmission, there would be a space. There would be a space before the first character of the next transmission. Okay. Now, what if the user typed ABC space EFG space send? Okay. Then what will happen is there will be a space. There is a deliberately typed space at the end of the first message that will appear, and then you are still inserting a space between 2 messages. So you will see 2 spaces then. Okay. Just exercise discretion on some of these things. I mean, the space is a trickier one to handle. So
Can we change or put some more things in this thing that you give us?
this file should not be messed with at all. Okay, you should not be altering this file. All you should be doing is to put your design under MCTX and MCRX, and if you need additional subcircuits, you can create them right in this file and incorporate them in MCTX and MCRX. Okay, so but this file you should not change in any way. In fact, you should not even rely on that this file will be there for you. We may replace it with a alternate file and test your design with it. Okay, so we'll only be looking at your MCTX and MCRX and any subcircuits they are using.
But once I press send, the keyboard is going to send one letter as a one.
No, keyboard is not going to send anything if you press the send button. The send button is totally independent of the keyboard. The send button is telling your design that the user wishes to send the message. Then you have to, at that stage, your state machine has to now start reading from the keyboard. Okay, the keyboard and the send button are 2 independent things. Okay, there's a question there first. Yeah.
Oh no. All right. So I'm still looking for some.
You're still looking for?
I'm still looking.
Okay.
So say if I were to type like +0, like all 32, right? Would it be that? Say I have the convention where my space is like 7 0.
Mm-hmm.
Does it mean that every 7 would be united to the entire space?
You're talking about the zeros I typed on the keyboard?
Yeah, like all zeros. Regular.
Yeah, but remember the zeros I'm typing on the keyboard and the zeros we are talking about on the Morse code are 2 different things. Right? The zeros I'm typing out here is the ASCII letter 0.
Okay.
right? Whereas the zeros that we are talking about are the 1-bit value of 0 or 1. They're different. Okay? Question.
So how tight must the clock tolerances be in that if we want to set it to say like 10 clock cycles for each like space, can it be like, are we allowed to say like between 9 and 11, or must it be like exactly 10?
Oh, you're saying if we say a dot is a 10 clock cycle, then
Right.
yeah, it should be precisely that.
Okay.
Yeah. Otherwise, we cannot test it. Like if you start saying that, oh, it could be in the range of 9 to 11 and all, it's going to be just horrendously complicated. So all we are going to let you do is to tell us what your n is, and we are going to test for that. Okay?
Is there a way to multiply like the speed of the clock? So if you give it like
No, there is no way you can multiply the speed of the clock. You cannot multiply the speed of the clock. And in any case, we are giving you 2 clocks of identical speeds. Okay? Identical periods, yeah.
To elaborate on the spec, you said we will provide the n, and then you will test with that n.
Right.
You will not be providing us with an n, and we have to account for all
The n is your design choice. Okay? And in fact, n equal to 1 works perfectly fine. The only thing is, if you have a somewhat slackily designed FSM, it may be that you need n equal to 2 or 3. Okay.
And in effect, you said that active design would be considered better. So I was just that idea. What would you consider
N equal to 1 is fast. Right? Because I mean, n equal to 1 is sending at the fastest possible rate. I cannot send any faster than that. So a DIT.
That's like the idea to strive for? Or?
Yeah, and it's easily done. I don't know. What kind of n are you using?
1.
1. Okay. See, existence proof. And what about your design? N equal to 1. So we have 2 designs with n equal to 1. I don't have any with higher n. You have variable n, sounds like. You have a variable n design, or no? We were asking.
No, I'm just saying like
Okay.
if we had higher end, now it gives us a little bit of tolerance.
Yeah. So you can. So higher n can make your design easier, but the transmission slower. Any further questions? So now I also sort of realized that some of you are totally lost in step number 1, and so I wanted to kind of help you along a little bit by suggesting the way you can approach this design, hopefully. Okay, but before that, I do any question? Okay, so how might and again the thing is this is a design problem, so there's no one right way or wrong way. Okay, I mean. You can approach it from a state machine diagram perspective, from a data path perspective, some combination thereof and all. I'm going to throw one possibility at you. And if you're totally lost, feel free to adopt it. But this is just a sketch, bear in mind. Okay. So what will happen out here is something like the following. Okay. So think of your design as really having kind of 2 parts to it. So remember, I have a keyboard and the send button, right, which I'm interacting with. Think of your design as having 2 parts. One is kind of a controller, which is going to orchestrate things. So this is a controller. It's going to orchestrate things. So it is going to read this signal, it's going to read this signal. Keyboard also has a data coming. That's a 7-bit data. And what I'm going to do is I'm going to create a data path. And what this data path does is the following. It takes this character, and it has access to this character, and I'm going to tell it go. And what it's going to do is it's going to take this character and send it out in Morse code form. Okay, so there's some sort of a go signal. And we saw this pattern in the vending machine example or the lock example. And when it is done, it is going to send me the done signal. And it is the one which is driving this 1-bit wire. Now, so this data path is the one which is going to do the encoding and all. Okay. So one way I thought about this design was the following: that let's look. So what's happening? I have a 7-bit ASCII character. What's the longest Morse code that I have? Anyone? 5 dashes. Okay. So 5 dashes. So that's 3, a space of 1, 3, a space of 1, 3, 1, 3, 1, 3. Now after that, there is going to be inter-letter space, which is how much? 3. Okay. So I have a space of 3. Okay. Now we add this thing up. How much is this? 22. So in worst case, I have to send a pattern of 22 some zeros and ones. Okay. So one way I can think about it is that instead of decoding my ASCII character to the way I was doing in the homework, number 2, ASCII to a 10-bit pattern, I'm going to take each ASCII letter and map it to a 22-bit pattern. Now, unfortunately, that's not enough because the characters are of different duration. Some of them occupy all 22, but some of them may not. So I'll also have, since it's 22, I can have up to 5 bits. So I need 5 bits of length. So imagine that I have some combinational circuit which takes the 7-bit and produces these 27 bits. Length plus this pattern. And for certain characters, some of these patterns are unused, so I'm just going to put a 0 there. That don't cares. Everyone okay with it thus far? Okay, so 22-bit of pattern, worst case, and 5-bit of length. Okay. So, and designing that combinational logic is just a gigantic ROM. Okay, so you don't have to. I mean, it's 128 locations of 27 things, and actually Logisim conveniently lets you load it from a file, so you can edit in a file, write a little script to do it, create the file, just load it in. Okay. So let's imagine now I have such a combinational logic. I have a combinational logic which takes my ASCII character, dumps out these 27 bits. Now, next thing that I'm going to do is let's look at what this controller will have to do. And how this controller and how this sending thing is actually going to work out. So now I have this magical combinational logic, which is taking the 7-bit signal, which is sending out a 5-bit length and a 22-bit pattern. What I'm going to do is I'm going to feed it into a shift register. Recall a shift register, I can load it in parallel, and then every clock tick, it ticks out 1 bit. Okay. So I'm going to load it into this. Of course, I now also need to control, so it will have a load signal, and it has a serial out, in which one by one the signals are going to go out. Okay. Now the thing is, obviously, I cannot shift out all the 22 bits because they don't make sense. Some characters are smaller, some characters are bigger. So what I'm going to do is I'm going to take these 5 bits and I'm going to make this thing. I have to kind of come up with a done signal. So kind of intuitively, what I'm going to do is every time I'm done with the transmitting a character, my controller is going to command this thing to load the next character. Okay. So what I'm going to do is I'm going to take this thing. I'm going to feed this guy into a register, which will also have a load signal of some form. So I have 2 load signals. So after I'm done with every character, I'm going to load the specs, and I'm going to feed this thing into a loadable counter. So this counter is going to have some sort of a reset signal. So the idea is that actually no, let's take it back. Okay. I'm going to take this and I'm going to have a second thing which is a counter, and I'm going to have a reset signal for this counter. Okay, again you can design a counter like this, which I reset it. Okay, so at the beginning, every time I'm loading a new character, I'm loading its pattern, I'm loading its length, and I'm resetting the counter. And then in the successive clock ticks, the counter will tick up until, and I want to keep letting it tick up until the length is encountered. So I want to have a comparator out here. and that will give me my done signal. Okay, so you can think of this load, and this reset is kind of like my go signal. I'm going to make go high for a single clock cycle. That takes the next character, and then I'm going to wait for the done signal for it to be done. And the effect of that would be that out of this shift register, length number of bits are going to be sent out. Otherwise, I wish to send zeros, so I'm going to put a little multiplexer out here whose other input is 0. So when I'm not sending anything out, I'm going to exercise control over this mux to send out a 0. Right? So this data path does bulk of the work already, which is I can tell it, give it a character, I can say go, it will send out the pattern, and when it is done, I have an ability to then switch to shipping out zeros. Okay, then comes my controller part. So my controller now has to, if I go back to the previous slide, my controller has to interact with the button. Button is straightforward. It's a binary signal, 1 bit. Whenever it's high, we know I have to start working. The keyboard is a trickier interaction. Okay, so keyboard has a signal coming to us which says there is something available, and then we have to tell the keyboard pop out the signal. Now popping out of the, telling the keyboard I'm done with the current signal, how can you do that in my design? Which signal would you use to tell the keyboard I'm done? No, actually go, because once I'm done loading, I'm done. Right? So I assert go. In that cycle, I'm loading the current character into these registers, and after that, I don't need it. Right? So I can do that with go. So this go can also go to the keyboard to what was it? Read enable or what? Yeah, read enable. So it can also go to the read enable signal. Okay, so in one go, I can kind of accomplish all these things. I can current character out of the keyboard, I can load it out here, and I can tell the keyboard I'm done, shift it out. Question on this? Everyone clear on this pattern? Okay, let's move to the state machine. Now, one thing is the following, that the goal is to keep the control state machine simple. We don't, I mean, I could have done another design where the control state machine was handling everything, the bunch of possibilities, but I started out with that something which is very simple. So what's happening in the control machine? Well, when I start out, I'm kind of in a wait state. I'm waiting for what? Anyone? And what else? Just because send is high, is that enough? Huh? Available, right? So there are two conditions. Send should be high and keyboard should say available. So you can say send and available. Go ahead.
Why do you need available? The keyboard sends 0000 by default. So.
Yeah, okay. Good. If it didn't, I would be messed up. Okay, but you're right. Okay. So, if this is happening, then I'm going to make go equal to 1 on this transition. Okay, so when this condition is true, I want to load, and else I'm spinning out here and go equal to 0. Okay, now I go to the next state. Now in the next state, what has happened is I have done go equal to 1, so I have loaded things. Now what am I doing? I'm going to stay. So this is where I'm kind of, so this is wait for message, and here I'm going to wait for letter done. Now, as long as done is false, I know the letter is being transmitted. And while that is the case, go remains 0. Now at some stage, done will come. And now there are two possibilities. I have additional characters to send. So that you can think of either another edge you can modify these things. I'm going to just operate that a second loopback condition is that I am done and available is true. If that's the case, I'll make go equal to 1. And you can merge these two loopback into a single condition. Okay. And alternatively, if done has happened but available is false, then I go back with a go equal to 0. And that's my controller. Okay, I need exactly one flip-flop with a whole bunch of logic around it. So I mean, you don't just a very trivial controller, and bottom side is my data path. And other than the pain of going through designing this combinational logic, everything else is actually in Logisim. I don't know if Logisim has a shift register. Anyone? It does. Okay, so shift register is there. So all the modules are there. You're done. Okay. Questions?
What about like send? Like you're still holding send, it shouldn't go, right? Because you don't want to start until.
Yeah. Okay. So I guess here I kind of made the. So you would also maybe then say, yeah, you're right. Okay. So if the what he's pointing out is if the user keeps pressing the send, I'm going to have trouble. Okay. So what I can do is I can. One possibility is I can introduce a third state, and I can spin there as long as send was pressed and then come out of it. So yeah, that case I'm not handling. So I'm still going to leave some stuff for you guys to handle. Okay.
So what controls the 0 versus?
Oh, okay. So essentially, whenever I'm in this wait state, I'm going to make the zeros go out. Whenever I'm out here, I'm going to go this guy go out. Okay. So you can have that signal coming into.
The 5-bit signal, that's like a binary value representing how many characters.
How many bits out of those 22 I need to actually send out, right?
And what's the is that a D flip-flop that the 5 is going into?
Yeah, this is registered 5-bit D flip.
What is that for?
Because I want to remember, I have told the keyboard that I'm done, right? So as soon as this go signal also goes to the read enable of the keyboard. So as soon as I do go, the keyboard output will potentially change, and that will percolate through my combination logic and change this. So if I do not have this register, it will affect my comparator. So so this is basically the state. This is basically saying this is these two registers together. The shift register in this guy is collectively saying this is the state of the letter. So at every time I say go, I load the spec for a current letter, and then this guy can change, this input can change, I will be unaffected. Okay. So that's what's going on.
And for the counter, shouldn't you have an input into the counter? So I see you have a reset.
Reset, yeah. I mean, I don't remember whether Logisim counter has a reset or not. This needs to be a synchronous reset, so you have to be careful. If the Logisim counter has an asynchronous reset, then you will have to create a synchronous reset counter, which is again straightforward. So, okay.
But I mean, like, what's feeding into the counter? Like, there's nothing feeding.
Nothing feeding. It's just counter. So binary counter it counts up. It by default it just keeps counting up, rolls over. All I do is that whenever I say go, I set it to all zeros. Okay. Now I have not thought through carefully. It may be that instead of encoding length out here, you may have to load length -1. I don't know how. I have to think through it more carefully, but essentially this kind of approach would be a clean way of doing it.
Can you just repeat what you said about the 5-bit and the register?
Yeah, so what I was saying was the following, that when I say go, then I've loaded the shift register, and let's say this register up here was not there. What will happen is the effect of this go also is it's telling the keyboard now you can throw out the current character. So the keyboard will remove the frontmost character and this value will change. And therefore the output of the combination logic will change right after, as soon as go goes high. And so if I were to not have this register, I would start getting the length of the next character, next letter to transmit, which is not what I want. So I need to hold it also. So go makes me remember kind of this. Think of it like this is a specification of the current task that this side is doing. Pardon me? Oh, of course, yeah. But it cannot count up. So clock is implied. I mean, yeah, everywhere, wherever it's needed. No, not here. Sorry, here. Clock here. There's a clock here. There's a clock here, and of course there's a clock on this.
If you encounter like a letter and a space,
Mhm.
do you have to put the three zeros, meaning that's the end of a letter, and then space, so meaning 10 zeros?
No. So if it is end of a word, then it's 7 spaces if you're using that scheme.
So you don't want to put those 3.
In that case, you won't put those 3s. So another way of thinking about it is that the space in my case will become 4 spaces, four zeros instead of 7 zeros. So I can make that every letter has a three zeros at the end because that's the policy I'm using. So now if I have a letter followed by a space, then the space will have 4 zeros associated with it. That's one way of looking at it. Okay. Does that make sense?
Yeah.
Okay. So I've given those of you who are kind of totally stuck on step 1. Hopefully, this is of help. And the key thing, and I would like you to think about the receiver part in a similar way, in that think about how you can divide things up into kind of the data side and the control side. Don't make controller super complicated. Part of it is just a practical issue, which is if there are too many states, then FISM output is going to be horrendously complicated. And since we do not have a completely automated chain, because EDA Playground gives you the logic, and more the logic out there, the more horrendously complicated the netlist is going to be. So something like this can work. Now, there are alternative designs. I mean, I relied quite a bit out on the data path. I could have something where the data path was very simple and the controller was more complicated. Go ahead.
If I didn't use this in the Verilog at all, could I just like submit like my drawings and state diagrams and pre-code and stuff?
Yeah, that should actually not just can, you have to. Yeah. So basically for data paths, you should give the pseudocode-like description of the next state and output function. And for controllers, you have to draw these kind of diagrams. Okay.
Wait, in this case, we said Go is supposed to be an input.
Hmm?
Go is supposed to be an input because Go is controlling the load, the reset.
Go is coming from this,
from the
state, from the controller into the data path, but it's feeding to a lot of places. It's also going to the keyboard.
Yeah, but I thought earlier we said this was going to tell you when it's, oh, it tells you when it's done. Okay,
Done is going to the controller, and go is coming from the controller. Okay. So this go done paradigm is a very useful one because that's what lets you deal with things which can take arbitrary amount of time. Our problem out here was that this side, the transmission can take different number of clock cycles. So I have to deal with it with this kind of a pattern that I say go and then wait for the done, and then I need to have some logic, which is this counter plus comparator, which tells me when things are done. But again, I must emphasize, I mean, look, this is one out of any number of designs. I mean, I don't know what kind of design you have.
For the transmitter,
Yeah, for a transmitter.
I do the combination logic thing is exactly what I do.
Exactly what I've done. Okay.
Instead of using a shift register, I
Uh-huh.
use a mux. And
Okay.
use a counter, I just select logic for the mux.
Okay.
So it goes like 0, 1.
Okay.
The next.
What's your design like?
It is really stupid.
Nothing is stupid.
I implement every case.
You implemented every case? Okay, and that's fine too.
It's really stupid.
That's fine too. Okay, look, I mean, again, I'm coming at this problem from years of experience. Okay, so of course, but point I'm just trying to make is we're not going to worry about the stupidity of the design factor in the grading. Okay, its functionality is what matters. Okay, so as long as it does the job. Anyone else who is sort of, you were saying that kind of working, so
Kind of like that.
kind of like that. Okay.
I changed like the 10-bit morphs and looked at like 2 bits at a time. Kind of like,
Okay, so you're doing that. Yeah, I thought about that approach too. I think that can also work nicely. But anyway, this seemed to be the conceptually the easiest way, but it does require you to throw away everything you did for homework number 2.
You just need like a controller like you have, and your transmitter can be from homework 2.
Yeah, you could. So you could imagine that instead of this approach, so like what he's suggesting at the back, instead of this kind of a fully decoded 22-bit thing, I can take the homework number 2 10-bit outcoding and kind of walk through that. Yeah, you could do that too. So again, no one right answer, but I was kind of getting worried that some of you were, I've spent 30 hours and nothing. Okay, so firstly, bit of good news when I arrived was that there were actually at least 2 people who were silent on Piazza, but they actually have working design, so that's great. And some more seems like partially working design, so that's hopeful sign. But hopefully the rest of you, this will give you a start. Now, MCRX, I would like you to think about it, how to approach it. It's actually the simpler ones of the two. So I have presented you the design for the harder part of the assignment. Okay, questions? Oh, you don't think it's a simpler?
No.
No? Okay,
I'm kind of more confused on MCRX, but I haven't spent much time on it. So.
okay. So, kind of a hand wavy idea to throw at it. Think of it a little bit in the reverse direction. Bits are coming in, you feed them into a serial to parallel converter. So they are feeding in serially, and at any given point, so essentially they're going through a chain of flip flops. And at any given point in time, you have a snapshot at parallel of a whole bunch of bits, and you're looking for certain patterns in it. Okay, and in particular, we know that a letter ends when we see 3 zeros in a row. Okay, so at the time I see 3 zeros in a row, and let's imagine I had 22 flip-flops like that in the worst case, then I can basically feed them into some sort of a gigantic complicated combinational logic and do my task. That's one approach. Okay, but think about others. I mean, there are a bunch of other possibilities as well. The other way, just a sec, the other way I can do is I can monitor in my state machine bit by bit by bit. Okay, so every time I see a dot or a dash, I kind of keep feeding them and then feed them into my homework 2 logic. And the dot dat decision could be done by observing 0 to 1 transition in the 1 to 0 transition. So you could approach it that way also. So maybe I'm wrong. Maybe it's more complicated. Okay, I think that, let's say, comparable complexity.
So is there a time requirement in that how quickly you have to display after
No.
you receive the signal?
No. There is no requirement on that, and likewise there is no requirement on actually how much time after I press the send button you have to do it either, as long as it's humanly tolerable. Okay.
What is the, there's also an assumption as far as the minimum clock cycles that the send buttons would be pressed?
So send button would be pressed for at least 1 clock cycle. Yeah. But given that we are going to be running it with a high enough clock frequency within LogSim, it will likely be pressed for multiple actually, which is the issue that he was raising, which is I was not addressing the case that all of this happened and the send button is still pressed. Okay, so I need to take care of that.
Oh, so in all of them, send is 1.
Well, no, so the issue will happen as the following. I press the send button and then I just keep pressing it. Okay, so what will happen in this case is that it will come back out here and it will, if my original state machine, so it will come back out here, it will see send and perhaps no available, so it may still work out. Yeah, I think I need to think through it, but the case he was worried about was I just keep pressing the send. Okay, what will happen in that case? I mean, you could also imagine that I just tie send equal to 1, in which case what will happen is as soon as I type a character, it will be sent out. Right? So in that case, I'm basically never assembling a message. I type a character, it disappears. I type a character, it disappears because the machine is up.
Is that desired or is that not?
Well, the reason I created the send one was that you can type a message, you can edit it, and then press the, because the keyboard actually allows editing also. You can do deletes and stuff like that. So this is what kind of a more realistic machine is going to look like. Type it, say send. Okay, but you could imagine that the send button was conceptually always pressed, in which case the moment I press a character, it's going to get shipped out.
Right, but if you were to do a self-back loop with the send, then that would mean that if you
actually,
have to let go.
The more I'm thinking about it, I don't think it might even be needed. Okay, because if let's say the send was continuously pressed. Okay, so what will happen now is effectively available is going to drive my whole circuitry. Okay, so if there is nothing available, I'm going to stay put in this wait state. And as soon as the user types something, available is going to go high. I'm going to move out here, transmit something. So I think it probably still works out. Further questions? Let's see. Okay, so those of you again who were stuck, I'll post this slide, these 2-3 slides, so you will have access to it. You can adapt this thing and work out, work from this. So hopefully it gives you somewhat of a starting point. Okay, so a bit of a recap of what we were doing last time. Oh, and one other thing, there is a makeup lecture tomorrow. Just remember that at 6. So what my hope is that I should be done by the material by the Monday's lecture. So next week I will do Wednesday as kind of a finals review, answer your questions and all, recap. And also I have another extra time slot on Friday 6 to 8, which again we'll use for that purpose. Okay, so just yeah, I actually was preparing it this afternoon. It should be out by later this evening. And just to let you know what it is going to be about is, so it's essentially designing a arithmetic logic unit. Okay, and what will, so essentially you have to specify opcodes, you have inputs coming, you have to do those operations, and the tricky part there is that you have to implement multiplication and division, but without using the multiplier and the divider in Logisim. So you have to do the hard way of repeated repeated add or repeated subtraction in different clock cycles.
Yeah, so just for a quick recap, how does the grading for the fourth design assignment?
Yeah, so what will happen is if you do the fourth design assignment, then the weight for the final goes down and the weight for the design assignment goes up. It was in the very first lecture, I forgot. So you can look there. Okay. And again, this is a decision you have to make upfront, so you cannot do both and then pick the best.
Can we see the project before?
Oh yeah, the results of the project.
No.
Oh yeah, we'll yeah, it will be out tonight.
No.
Okay.
Is there a reason why we don't get to pick like the highest or the higher of the two? Because
I think I want to keep it fair for those who choose not to do the homework.
Right. So.
Okay, so I basically, if you're confident about your design skills, go for it. And there's plenty of time. See, the other issue is final exam is just concentrated, where here you are going to have a bunch of days. So I feel that it is fairer that those who are choosing to do, then they make a conscious decision. Okay. And you know whether it's working or not. Unlike the final exam where you don't know whether your answer is correct or not, here you actually, if it's working, you know it's working. And if you totally mess up, let's say in this design assignment, don't submit.
Well, like say you think it works, but then you actually like really.
Come on. You can always test for addition, subtraction, division, and stuff like that, right? There's nothing magical. I mean, at this stage, you should not be massively wrong. So, or you should know whether you are massively wrong. So, okay.
Most of it was like.
Huh? Yeah. Okay. Go ahead.
What's the deadline of the assignment?
It would be the end of like the weekend before the final, basically. We can, so it will be before the finals. I think the finals are on Monday, if I recall right, or Tuesday, right? Yeah. So I'll probably keep it on Saturday or Sunday or something like that. I don't know. Any votes? It has to be before the final exam. Saturday midnight? Huh? What is it? Sunday midnight? Okay,
so
well.
Monday to decide, like.
this out before.
Yeah.
No, but the flip side is you still have to take the final. So I don't want you to be just stuck with this design assignment. Okay, I'll keep it Monday midnight. Okay, fine. So you can decide, and if you think that you have done a good job, submit it. If not, don't submit it. Okay, but once you submit, it's an irrevocable decision, and that's it. Okay. Uh, okay, there were some other hands raised. Any additional questions? Okay, so. Uh, So last time around, and I guess I kind of realized that I was having a pretty hard time getting some of these concepts across last time. So let's take another attempt. Basic idea we were looking at was that when we are designing these finite state machines, the control FSMs, if you may, then their next state logic and output logic, we could implement it using a ROM. And a ROM is nothing but a convenient way of implementing a combinational logic. So what we were doing were that where our next state and logic and output logic used to sit, we basically put a memory, ROM, RAM, whatever, and essentially the state bits plus the external inputs become the address, and the output is the next state and the output bits. And then we realized that the problem with this is lots of bits. 2 to the power s plus I, that many locations, and each location has s plus o bits. And we kind of saw that in this example also. So I'm kind of jumping through the slides a little bit. What we saw in this case is that oftentimes what's happening is that I have rows which are essentially identical because in those states the input had no effect, for example. And the other pattern that we were also noticing was that most of the time, in a lot of these state machines, we just move from one state to another state to another state, and once in a while we branch off. Okay, much like our programs, that most of the time we move from one statement to the next statement in the program, and once in a while we do a jump or a if then else or a while loop or something like that. So the set of things that we did last time revolved around that how could we optimize the size of this memory. And to highlight another example of this nature, so this was this enhanced traffic light controller where we added things like I'm spending multiple clock cycles while the light is green in north-south direction. We were also letting all the cars on east-west go through, and additional and we had the state extra state REW and RNS where all the lights were red, both north, south, and east were red. And then we had looked at again the state diagram for this where I had 4 bits of state because out here we have excuse me. So we have 4 bits of address. So we have 3 bits of state and 1 bit of the sensor value. So that's what we are getting out here. So state plus car east west make the address, and then we had the next state and the output, and they together constituted the data. So essentially, in my memory, the addresses are formed by concatenating my inputs with the state bits, and the data values were formed by concatenating the state bits with the outputs. And the problems we noticed were things like a lot of these rows are redundant. I add one additional input and suddenly my memory will blow up by a factor of 2. So a lot of time we spent last time around was to ways in which we can optimize this. So the first insight was that we can do what we see at in processors, namely there is this counter which maintains what is the next address in the program, where would the next instruction come from. So the contents of the memory are kind of like the instructions for a state machine. They're telling me what to output, what the next state is. So this microprogram counter is basically a special register which most of the time just increments. Every time I do a state transition, it increments by 1, but I also have the ability to modify it in other ways. So a more general structure than we presented was this, that microprogram counter gives me the address from which the current instruction is being fetched. So it tells me the address of the memory. But then when I update the microprogram counter, I can either add 1 to it, So that's the top one. Or I can load a totally fresh random value into it, and that value comes from my instruction, comes from the data in the memory. And then finally, I can load 0 to it if I want to initialize it to 0. Um, and then the idea is that there is some combination logic, which we also get to design, which makes use of both external inputs as well as a special field, again coming from the memory. So if you think of this word in the memory as an instruction, then there is a special field in the instruction which we call as the branch instruction. Okay, so the branching part of this also feeds back out here, and together the input and that branch bits, they decide which one of these options to pick. Should I increment the microprogram counter? Should I load a value from it which is coming from the instruction itself? Or do I just load a 0 out here? So as a designer, you have you have control over the branch logic. So you get to define what the format of the data word is. How many, what is the size, the next state will be decided by, is the same as the program counter, but you also get to decide how many bits I have for this branching logic. Now I can have no bits. It's possible that I have no branching logic, in which case this guy disappears. There are no branch instructions coming in which case my mux is being controlled entirely by the inputs. Or I can have more sophisticated ways of selecting the mux. The advantage of this structure is that the number of inputs, only affect the complexity of the branching logic. They are not affecting how many addresses I have in the memory. The number of addresses in the memory are only affected by the number of states I have. So instead of 2 to the power s plus I locations in the memory, I only have 2 to the power s locations. But it is coming at the cost that I have this additional logic. But now if, let's say, I introduce an additional input, an extra sensor, for example, this logic will become more complicated, maybe some few more gates, but my memory does not blow up by a factor of 2 every time I add a bit. So as when designing using this kind of approach, the high level view is like this, that I have memory, I have this program counter, I have a mux. Program counter can be incremented or can get some other values. I have this branch logic. I get to decide the branch logic, and I get to decide the format of the data word. So the output part of the data word is sort of obvious. The next state part of the data word is obvious, depends upon the branching part. What is the branch instruction is something that we get to design. And part of the design process is look at the nature of your state machine and kind of see what are the different ways I branch. So usually in your state machine, you're jumping from state to one state to next state to one next state, and it's the inputs which control if you branch. So like you may say at some state, if the sensor is 0, stay in the current state, otherwise move to the next state. So we saw that logic with the car east-west sensor. So there are similar kind of patterns which emerge. So this kind of makes sense that it's the inputs which get to control the branching logic, and then the branch instruction gives us different ways in which the input can affect things. So the design process then becomes that you first have to decide what your memory contents look like. Each word in the memory has 3 fields. It has a branch instruction, it has the branch target, which is possible value for the next state, next address in the memory, and then you have the outputs, which basically go out and control lights or other actuators. So, and then we kind of talked about what are the different ways we could structure these things. So I had a few examples. So let's imagine that what I have done is that I've created this kind of a design where I have the microprogram counter and I have a 2-input multiplexer in front, which gives me 2 options. One is that I can increment the program counter, and the other is I can jump to the branch target. So I can basically jump to the branch target, and I now get to control under what conditions I can jump to the branch target. So this branch logic is getting 2 sets of inputs. It's getting the branch instruction from the memory, and it is also getting my external sensor. So in the car example, in the traffic light example, we have the car east-west sensor, and I have 1 bit let's say to start with. So, so in my memory, in my each memory word, branch instruction is 1 bit. It basically tells me whether it's a branch instruction or not. I have a branch target and I have the output. Okay, so what I want to do is, if I don't intend to branch, if I just want to microprogram counter to increment by 1, then I'll make the branch instruction 0. But if I do want to branch, then I'm going to make the branch instruction to be 1. So the logic then becomes, if branch instruction bit is 1, and I want to say if car east west sensor is 0, then increment the program counter, otherwise jump to the branch target. So in this particular case, if we recall last time around, this corresponded to a NAND gate with an inverter at the input. But I can have other kind of logics out here. So a decision we end up having to make is how many bits to allocate out here. If a single bit gives me the option of branch or no branch, but branch under some condition. The condition can depend upon the input. So essentially, if b equal to 1, then I essentially have the instructions of the following form. It's basically saying branch if some function of input is true. Okay, else micro PC is equal to micro PC plus 1. Okay, so so it's to reformulate it is basically saying if input is true, then micro PC is equal to branch target. Else micro PC is micro PC plus 1. And this f input is what is part of my branch logic combinational circuit. If on the other hand b is equal to 0, then it basically says micro PC is micro PC plus 1. So that's the functionality which is being implemented out here. It's basically saying that micro PC, if branch is true, the branch bit is true, then micro PC gets the value of branch target if some function of input is true. Otherwise, it gets the next value. And if branch bit is 0, then micro PC always gets the value micro PC plus 1. So this could be one possible design that one could do, for example. So using this, I could express things like branch if car east west, or I could design things like branch if not car east west. So I can basically have instructions to say jump depending upon some condition based upon the input. So jump if sensor 1 is high, jump if sensor 2 is high, jump if sensor 1 and sensor 2 are high, things like that. So let's say in this example, or in some other example, let's say I had two sensors, sensor 1 and sensor 2. And I notice in my state machine that my jumps happen whenever sensor 1 and sensor 2 are both high. Then I could create an instruction of the form saying branch if sensor 1 and sensor 2 are both high. In that case, I would make my f, this function, which is function of sensor 1 and sensor 2, to be an AND gate. So I would basically say, I'm looking at my state machine, I see that the type of jump I'm seeing is the type where both sensor 1 and sensor 2 are high, and therefore I should have an instruction of the form branch if sensor 1 and sensor 2 are both true, and then I'm going to put that AND gate as part of my f. That would be part of that combinational logic. So I'm custom designing a jump logic. Let's say I design a different system and I see now, hypothetically, let's say I had 10 sensors, 10 1-bit sensors feeding in, and I want to say if majority of the sensors are true, then jump. Let's say I see that pattern. Okay, so what I could do is I can design an f, which is the majority function. And then I could say micro PC is if majority of the inputs are true, then go to branch target, otherwise go to the next thing. So you get to design the F, which is another way of saying is you get to design this branch logic. And okay, so you get to you get to design the branch logic. Now, why does that matter? Okay, so let's go to the yay part. Why does it matter? Okay, so anyone? So let's say all I had was the ability to say branch to an instruction, branch to an address, and I didn't have the ability to. Let's take the majority one. Okay, so let's say I had these 10 sensors, and what I gave you were branch instruction which could jump based upon individual sensors. So you could say branch if sensor 1 is true. You could say branch if sensor 2 is true, and branch if all the way to sensor 10 is true. But what you really needed is branch if you want to do something if majority of the sensors are true. So how would you encode that logic if I only gave you branch on individual sensors? So let's say we're writing a piece of software, and let's say the only statement allowed was if sensor number I, then this, otherwise something else. But what you are seeking to do is that if majority of the sensors are high, do something. So keep and count and all right. And what will be the penalty of it? I will spend many states. So my states will grow up, right? So by creating custom branch instructions, I can collapse the state. So if I see that in my state machine, the only branch pattern which is occurring is majority of the sensors are high, then jump, then instead of checking sensors one at a time, spending a state, so additional clock cycle on each one of them, I can create this branch logic which does the majority function for me. So, but at the same time, what it lets you do is to kind of have this memory-based kind of design, which is easier than doing kind of a complicated combination logic, and then only custom combinational logic that you're designing is going to be the one associated with branch logic. So sole reason we are doing it is to optimize the size of the memory. Okay, I could always do memory only design and then have explicitly listed next states all the time. I don't even need branch logic in that case. I can just always explicitly list everything, but then the memory size will blow up. Okay, so I'm going to skip these designs a little bit. Yeah, so what then ends up happening is that if you are choosing this memory-based approach to finite state machine design, then one of the early decisions you'll have to make is that should I make next state explicit all the time, or should I make use of this microprogram counter? And if I make use of the microprogram counter, then what kind of branching I need? So it's going to be a bit of an iterative design that you look at your state machine and say what type of branchings are happening, and then based upon that you have to design the branch instruction. That's one approach. Alternatively, it could be that you may be given a data path, and you may be given a state machine with a predefined memory with a predefined instruction set. So the branch logic may already be defined for you, in which case the branch possibilities may already be given. So it could be that someone for this traffic light controller went ahead and gave you a state, gave you the branch logic and all, and said, you know, these are the things you have. You can not jump, you can always branch, you can branch if sensor 1 is true, you can branch if sensor 1 is false, you can branch if east-west sensor 2 is true, and branch if sensor 2 is false, and someone just gave to you. And now if you wanted to do branch if sensor 1 and sensor 2 are true, you'll have to sort of combine these things. If on the other hand, you knew that branch if both left-hand sensor and east-west sensor was occurring quite commonly, then you may just create a custom instruction for that. Okay, so it's almost like you're getting getting to design your own instruction set for a processor. That's and the other setting is you're given an instruction set and you are using that. So the latter model is the more common programming model, but when you're designing the hardware on your own, then you have to design both. Now, okay. So let's look at further optimizations that get done to reduce the memory size even more. So uh, sometimes what we end up facing are also these. Just give me a sec. Okay, so this example with the left turn signal and all, it had a 3-bit branch instruction. It had a 4-bit next state, so 4-bit address, and it had 9 bits of output. So we had 3, b equal to 3, s equal to 4, o equal to 9. And so the question then becomes, are there further games we can play to kind of optimize this thing furthermore? So one thing which is often done is that we support what are called as multi-way branches. So the multi-way branch, kind of the idea is that instead of just an if true, do this, otherwise do something else, instead of just a two-way thing, it is kind of like the switch statement in programming language, that I look at a few bits, and then based upon those values, I can do a bunch of different things. So it could be something like uh, look at the east-west and the left-turn sensor. If both are false, do jump to address 1. If left turn is true, east-west is false, jump to address 2, and the other 4 combinations. So you can think of that there are a bunch of cases, each one of them with their own target addresses. So um, the analogy, in those of you who are familiar with assembly language, would be that I should be able to say that if a 2-bit signal takes value 0, 0, jump to address 1. If it takes a value 0, 1, jump to address 2. If it takes a value 1, 0, jumps to address 3. If it takes a value 1, 1, jump to address 4. So I'm specifying 4 addresses corresponding to 4 conditions. If I had a 3-bit signal, I will have 8 addresses. So I want to specify in a single clock cycle options of branching multiple ways. That corresponds to having kind of like, if you think about it, in this case, I have 5 cases. So in some senses, that corresponds to, I'm in a state, and there are 5 possible transitions out of it to 5 different possible next states. So these next states correspond to what is happening in the each of the cases. So I want to do this kind of a multi-way branch. In the absence of a multi-way branch, I'll have to do things sequentially. So let's say I were to tell you that you are not allowed to have 5 outgoing transitions from a single state. You are only allowed to have 2 transitions, condition 1, condition 2. Then the only way I could implement something like this would be I would do 2 conditions, then perhaps branch on this, likewise and then finally kind of do this. So I can create a decision tree in effect, so jump from state to state to state until I have everything kind of explicitly enumerated. That would be very inefficient. So if I can do this multi-way, it would be a big win. So in a single memory address, I want to, in a single state, I want to specify, depending upon what the input conditions are, 5 possible next state values. So how would you do that in the memory? So I could expand the memory width. I can arrange for having 5 branch targets. What's the penalty? So let's say I have a 5-way branch I want to do in a given state. So I have 5 possible targets. Okay, one of them is the next one, so that's trivial. So I still have 4.
You would still need memory to store all the states.
Right. So if I have S bits, I need 4 S bits, and I need 4 S bits in every word, whether I need whether the other states I'm doing 5-way branch or not. Okay, so it will blow up the width of the memory considerably. So, any thoughts on how can I express 4 or multiple branch targets, multiple branch target addresses, but not have to list all of them, and still be able to do it in a single clock tick.
So like branch target and an offset.
Branch target and an offset, yeah. So any Anyone familiar with the concept of offset addresses? What does that mean?
So like in a switch statement,
Mhm.
you have it points to it has jump table
Mhm.
where VD is the offset to the input is the offset to the.
Right. So think of like the following. Let's say I had a variable x which can take 4 values 0, 1, 2, and 3. And I want to do different things depending upon what x is. These 4 values. Now in a switch statement, I can easily say switch x, case 0, case 1, case 2, case 3, and there, things are fine. But in our state machine, I now want to have a state where I say x equal to 0, go here, x equal to 1, go here, x equal to 2, go to a different state, and x equal to 3, I want to go to a different state. I want to do something like this. So I want to say jump to an address which is a function of x, right? So the address of my next state, because each one of these states corresponds to a memory address, is a function of x. So what I could do is I could basically say jump to some address plus x times, let's say 5. So if x is 0, it will jump to address. If x is 1, it will jump to address x plus 1. If x is 2, it will jump to address x plus 2, x plus 10, and so on and so forth. And so in my memory, I'm jumping to 5 or 4 different places, but I only have to specify address, and x is part of my branch logic. So x is some external input, so coming in, and so I can still say jump to address, but do a multi-way jump based upon x. And this x times 5 is part of my branch logic again. I get to be so the fact that I'm making use of this offset is part of my branch logic. As far as my instruction is concerned, I'm going to say do a multi-way jump to address, and but make use of x, and the choice of 5 is going to be a design choice. Question.
But if you do that, it becomes messy for the future. You can't just do increment the PC anymore.
So what will happen out here? So firstly, can I say increment? So increment the PC. So it could be, in this case, I could set address to be the next address, for example. That's a possibility. It could be that here there is a default case which maybe x is equal to 0 corresponds to increment the PC, and the other 3 correspond to this kind of a jump. So there are different ways you can kind of organize this thing. This 5 basically tells me that in my memory, I'm going to be jumping to address plus 5, address plus 10, address plus 15. And this 5 is basically saying whatever you wish to do for case x equal to 0, you have 5 instructions to do it. Whatever you wish to do for x equal to 1, you have another 5 instructions for doing it. If I were to make, instead of x times 5, I were to make it x times 1, then I would be jumping to address plus 1, address plus 2, address plus 3, depending upon the 4 cases. So how much work you have to do in a given case gets to decide what multiplicative factor you're going to pick. And x gets to decide what your different cases are. So let's look at an example, hopefully. So this is a system where what I have is I have a 2-bit input, and what I'm saying, I'm basically saying microprogram counter is microprogram counter plus branch target plus 4 times this 2-bit value. So what the effect of this thing would be that whenever I'm undertaking this branch, then I would either jump to micro PC plus branch target, or I would jump to micro PC plus branch target plus 4, or micro PC plus branch target plus 8, or micro PC plus branch target plus 12, depending upon the 4 possible values that in this 2-bit value can take. One other thing you have noticed out here is that I'm actually adding branch target to micro PC, as opposed to saying micro PC is branch target plus this. So I could, thus the other alternative could have been, I could have said micro PC is equal to branch target plus 4 times in 1:0. This is an alternative possibility. That micro PC is jumping to a branch target plus this, as opposed to micro PC is current value plus this. What trade-offs do you see between the two? So take design, second design. Let's say my micro PC was S bits. How many bits would the branch target need? Which is S. So you need S bits, right? Okay. In this case, first case, micro PC is S bit. This is S bits. How many bits can the branch target needs to be? It could be a lot smaller, right? I mean, basically, it will affect how far away I can jump, right? So if, for example, micro PC was 32 bits, then I don't. If I'm willing to live with the fact that my wherever I jump is going to be nearby, then instead of making branch target to be 32 bits, I can make it, let's say, 10 bits. And what it does is it basically says from wherever you are, your target target whatever possible stage that you're transitioning to should be within 1024 of you. Okay, so branch target could be a lot smaller. This could be much less than S. Possibly. Okay, what's the advantage?
Less memory.
Right, because in the memory, each word I store the branch target. I do not store the micro PC. So by making the branch target smaller, I can shrink the width of the memory. So with a design like this, with multi-way relative jump, okay, that's what this is multi-way branch. That's this part, and this thing is basically saying is relative jump. Relative branch. You are branching to an address which is an offset from your current address, as opposed to branching to an address which is an absolute address. Okay, because the absolute address, as in the second case, can take a lot of bits. So this is absolute. This is relative. Relative would be cheaper because I can have a less wide memory. So in many processors, even in the assembly level, you are going to see this kind of a capability because their address space is very large. Okay, but you do not want to make every instruction very large because that would be very memory intensive. So what we do is we always make it relative to current value or some other register, and we only specify the relative offset. So instead of saying that jump to address whatever 4,000,000,020, we basically say jump to 1,000 ahead of what my current address is. So I only need to specify that small offset. And in most cases, you can still kind of do pretty much what you want to do with something like this, because while this is smaller than S, but it's still, they tend to be large enough for you to be able to do that jumping that you want to do. So multi-way branch, relative branch, these are two concepts. So multi-way is not something you will typically see in assembly language level, but you would see it in the microcode level, or custom design kind of stuff. Relative jumping is quite sort of common. Yeah.
I think so. When you say micro PC, you're not putting that into memory. That's going to be a separate register. So it doesn't count.
Right. Because this is a separate register, and it's a single register, right? Because whereas branch target is present in every location in the memory. Okay, whether I use it or not, it's present. Okay, even if it is don't care, it is consuming transistors. So making it is important to make the branch target smaller, whereas micro PC could be bigger.
Right. Because like in the way that you wrote it out, it looks like all of it's in the memory.
No. If you go back out here, so it's branch target which is in the memory. Okay, so it serves me to keep branch target smaller because that saves me bits in every slot of the memory. Micro PC I can make arbitrarily larger, but of course it increases the number of words. Okay, so they're addressing different things. So micro PC tells me how many states in the program I have, whereas branch target tells me where I can put those states. If branch target was, if I had the second category where branch target was complete S bits, that means that I can make the code for a state sit anywhere in the memory. Whereas once I move to something like this, it's basically saying that if I'm in a state, I can only jump to nearby states, states which are located nearby in the memory. So it's constraining your design, but still leave you enough flexibility to do stuff that you want to be able to do. Okay. So another another additional optimization that begins to happen is the following, that we often notice that we don't need to branch a lot of time. It's not that in every state we are branching. Okay, most of the time we are just moving from one instruction to another. And thus far we are still carrying the baggage of branch target in every memory word. Now, how could we optimize that? Well, another realization that comes up is that outputs are changed relatively infrequently. So if you think when you write a program and let's say you are outputting some value, it's not that you are outputting in every statement you are changing your output values. Okay, if I have a lights in a traffic light controller example, the lights, any given light was changing in only some of the states. So it's not that I need a new value for the output in every state. So these two observations, then I do not branch in every state and I do not update all the outputs in every state. So could I reuse the bits? So the idea is that now instead of every instruction carrying both the output bits and the branching bits, what if I can say that now I'm doing branch or now I am updating the output? So kind of the concept becomes like the following. Okay. Imagine I have two types of words in my memory. One are the ones which say this tells me which state to move to, and the other basically says that these are the this tells me how to update the output. So imagine for a moment that the traffic light controller, the lights had a register. So instead of always outputting the values that the lights needed, if in a particular state I can say make the light red, and once I have done it, I don't have to do anything further until the next time I go to it. So the difference is, so let's imagine I'm controlling a light bulb, and it could be on or off. So one possibility is that every clock cycle, I am controlling the input to the light bulb, saying it's 0 or 1, on or off. But that means that every state, I need to have a dedicated output going to that light bulb. Or imagine something more complicated. If I were to control the color of that light bulb or intensity of that light bulb, and it can take 8 bits to do it, then every state I have to make sure those 8 bits are valid. So that can be very expensive. What if, alternatively, at the light bulb I had an 8-bit register? And then in some states I can basically say load a value into the register. And other states I don't do anything. Okay, I don't need to maintain any valid value going to the light because the light remembers what I previously wrote to it. So the mindset now becomes that I'm going to, instead of outputting a valid output value in every state, I'm going to load a value onto the output register, and then at other times I don't need to drive it. So what that gives me is the flexibility that instead of my original design, let's see if I, instead of my original design, where I had branch, we had branch target, and I had output all the times. What I can now do is I can have two types of words in the memory. Those which just give me branch and branch target, and those that just give me the output value. And I want to distinguish between the two based upon one bit. So there's one bit which basically says, which is a branch instruction, and this condition is basically a good old branch the BR bits that we used to have. So I have two types of memory words. One where the first bit is 1 and they tell me how to jump, and I have a second type of memory word which has a 0 and they tell me which output to update. So they can say light number 1, set its value to 20. Okay, and then the light remembers after that, so the output remembers. So there's a register out there. So in each instruction I can do this or this. So what that does is it reduces the width, because instead of this model where I had to carry all the bits all the time, I can now have a much less wide, a thinner instruction. What's the problem, or what's the disadvantage of this approach? Memory would be longer. Okay, that's one. What else?
It might take more than one clock cycle.
It will take more time, right? So memory would be longer because what used to be one instruction is now 4. Okay, and the other thing is it actually takes multiple clock cycles to do it, because instead of being able to jump and update the output in the same clock cycle, I now will need 2 clock cycles. I can, in any given state, I can either jump or I can update. I cannot do both. So I am giving up something, but the idea is it kind of leads, generally speaking, it leads to smaller amounts of bits in the memory, and again kind of saves space. So which is why usually if you look at assembly language of microprocessors, you would see that they have dedicated jump instructions. So in an instruction you can only jump, and there are instructions in which you can only do input and output. You cannot do both simultaneously. There are some exceptions in some rare processors, but generally speaking, you have 2 separate types of instructions that sort of drive this thing. Okay, so this is another. So the concept then comes out here that at the output I have these output registers, and then whenever the instruction, whenever the micro instruction is a load instruction, it basically gets to write in this output register, and at other time it gets to jump. So I basically get to decide whether, based upon one bit, whether I'm doing updating the microprogram counter or whether I'm updating the output. Okay, so this is an example from the traffic light controller where you could imagine. So earlier on, what we had was we had 9 wires going to the 9 lights directly from the combinational logic, directly from our output logic, whether it was gates or ROM based. But in this design, what I did was I put 3-bit registers in front of each traffic light, and then the output logic actually updates the registers. But then in cycles which it does nothing, the lights retain their value. So I don't have to keep 9 output wires active all the time out of my state machine. I can get away with a lot fewer wires going in. Okay. Okay, so what we have seen thus far is that we kind of originally we had state table, and from state table we would go to gate logic and all and implement our FSM. Then we saw that we go with state table and then implement everything into a ROM, but do it in a very inefficient fashion. And then by introducing this concept of branch instruction or branch and load, we basically begin to optimize the size of the memory. And if you look at, so microcode is not used directly in processors anymore, but in other type of chips and all, you can still see it. But what I described as microcode is pretty much like the instruction set of a processor. Okay, you see similar kind of features in the processor, and there are, so if you have done a class where you have seen assembly language, sort of this is very close to that. And there are also companies and all which sell you designs, kind of processor design, where you can customize the instruction. So just like I was talking about, you can create your own branch logic and all, you can design. For example, let's say there is some special functionality that you do quite a bit, you can always create an instruction corresponding to it. So you can create custom processors. The term which is often used is domain-specific processors or application-specific processors. So these are processors whose instruction sets are optimized or designed by you, catering to a particular application domain. So if you need to do a lot of, let's say, sine and cosine, then maybe you might want to have a processor which does sine and cosine in a single clock cycle, and then put hardware for that out here. Or for example, if you have an application where perhaps you had to do a lot of what I was saying, there are 10 sensors, and depending upon the majority of them, you have to jump one way or the other, and it's a very time critical application, maybe you might want to have a multi-way branch. So you can start with these processor templates which these companies sell, and then you can create your application specific processors of that. So that's the microcode story. Yeah.
Is that ARM?
No.
What's ARM?
So what is ARM? Okay, anyone knows what's ARM?
It's like a set of instructions.
Okay, so many answers. ARM is a company. It's came out of University of Southampton in UK. The main thing is it's a very nice lightweight design. ARM does not make hardware; it makes the Verilog for hardware. That's one way of thinking about it. Okay, so it defines the instruction set. That is, what are the instructions, and it creates these designs, and then it sells the designs to various companies who then make the hardware and put stuff in them. They have a couple of models. So companies like Apple, they are called as what are called as ARM architecture licensees. So what they've done is they have licensed the architecture, and then they create from scratch their own implementations. Most other companies, they're not architecture licensees. What they do is they get pre-built designs, like a Verilog design, for example, okay, and then they're allowed to just implement that particular Verilog design on their chip, but they're not allowed to modify it. They're not allowed to do anything from the scratch. So big companies like Apple or Qualcomm or Samsung, they are architecture licenses. A lot of others, basically, they get these what are called as IP cores, intellectual property cores. So these are basically designs which you just put on your chip or FPGA or whatnot. So ARM is a processor. Its claim to fame is very efficient, tiny, consumes low power, all those kind of nice things. Okay. Anyway, so see you guys tomorrow at 6.